Hi, my name is Matt Holliday and welcome back to my class on programming in Go. In this section, I'm going to talk about concurrency gotchas, and really two things. First, I want to talk about some of the concurrency gotchas that are generic. In other words, problems that happen when you build concurrent programs. And then I want to talk about gotchas that apply specifically to Go, the tools in Go that you need to watch out for. So I've got three slides I'm going to start off with. And there are all these slides that I like to put the black top with the red letters because they're scary. Okay? And the first is, let's start with the basics here, right? The most fundamental problem with concurrency is the race condition. Okay? And we've talked about that all through here. Okay? So a race condition is a problem we have to solve in a concurrent program. We either have to make sure we're not sharing anything, or that we're sharing things that are read-only, or that we protect the things that are shareable and modifiable. Okay, I think we've covered that one pretty thoroughly. So the next problem, and we've talked about a little bit, and I'll come back to it, is deadlock. Okay, there are a number of things that can happen when we start trying to control race conditions. And one of them is that we're so good at locking things up that we just lock up the whole program, and the program doesn't make any progress. And we'll look at a couple of ways that happens and how to deal with it. So Goroutine leaks we've already discussed. I showed about 10 minutes worth of probably what is the canonical example of how to have a Goroutine leak. And I'll show that again here very briefly. And it brings us to this important point that when we start a Goroutine, we should understand how it's going to stop and what's going to make it go away. Because the way resources leak in a Go program, usually either you leak a socket or you cause a Goroutine to hang up because it's waiting for something that can't happen. Okay? And actually, typically, if you leak sockets, you probably leak Goroutines also. But that's how you leak memory. They're almost always tied to a Goroutine that didn't go away. And then there are a few things with channels, and we talked about that, and we talked about this diagram I showed about channel operations, so I won't dwell on that. Okay. That brings us to a list of other things, and that's primarily what I'm going to talk about. Deadlock and these other things are what I'm going to talk about in this section. Now, I've listed a paper. It came out in April of 2019, or the preprint came out. And it's a great paper. It was presented at one of the major conferences that year on concurrency problems in Go. And I want to say a couple things about the paper. First of all, again, I like the paper. Okay? I think that some of the things that were shown in the paper, I mean, there are issues with using the tools in Go, particularly when you mix the new things like Goroutines, channels, and select with the old things like Mutexes. But I also think some of those bugs are simple bugs. And maybe they were written a number of years ago when there wasn't much training. So most people weren't trained on how to use Go. There weren't very many classes or books. Okay? I think a lot of those problems could be solved by reviews. The most useful tool to prevent problems in code is the peer review. And having an experienced person looking at the program, because a lot of these things, again, I think they're kind of simple and they should jump out at you. And the nice thing about that paper is it suggests, and I'm hoping there'll be more work in that direction, is that there may be possible to find some of these bugs with static analysis tools. By doing static analysis of the program before it even runs, it may be possible to identify, for example, certain simple cases where Goroutines get leaked. I'm just going to show this slide very briefly. We went through this already. I'm not going to try to illustrate this on the laptop or the playground, right? It's the basic concept of a data race. So here's an example, right? We have got a handler for our web server, and the handler does an unprotected increment, but we know that the web server will run handlers concurrently, and therefore on a machine with enough processors in parallel. So this is something we would have to fix. But we've talked about that already in depth. I want to talk about deadlock. We're going to do that in the playground. Now I've got an example program. It's going to lock up. When I run this, it's going to print start, and then it's going to crash because the deadlock detector detected deadlock. Say that 3 times fast. All right? Now, this is just a little bit more complicated than the previous example. I've added some crap here. I think just to sort of make it harder to see this. But the reality is, right, I'm waiting on some channel, and I start a Goroutine, and that Goroutine may or may not actually put something on a channel. And if they don't, well, the main program's never going to go forward. It's going to wait on something that's never going to happen. So it's a slightly different version. Sometimes we have the go routine waiting for something that can't happen, right? And actually both, because this channel is not buffered. And so the send and the receive have to go together, right? But we've just prevented, in this case, we passed false in for OK, so we're not putting anything on the channel, so the program just stops. Okay. Again, the nice thing is Go has a deadlock detector that will find many of these cases. It'll crash your program, but you'll find them. Okay, so this is a simple way to create deadlock, and again, we've talked about this one. So let's move on to this other one. And what I've got in here is I've got a mutex, and I'm going to start a couple of functions, and I'm going to wait for somebody to signal done. All right, one of these Go routines waits a little bit, locks, defers the unlock, prints signal, puts something in done. Fine, we're good. Unfortunately, the other one does a lock without an unlock. And when we run this, not surprisingly, it's going to fail. And some of you may have seen that before I even push the run button. Right? And of course, what we have to do is the most important thing about a lock is if we lock it, right, we have to make sure we unlock it. And defer is very handy. Defer is the best way to do that. Now, this second program is a bit more complicated. I do want to talk about this because this highlights one of the biggest drawbacks of the mutex. Okay? I said things about channels and select, you could compose them. There's no way to compose two mutexes. You can't say in one operation lock both. You can lock one and then lock the second one. But there's no way to say like simultaneously lock both. So I've got a program with two mutexes. Okay? And I've got my first Go routine, locks M1, waits a little bit, locks M2, and it's deferring the unlocks just fine. And then it prints something and signals on the done channel. And my second Go routine does more or less the same thing. But there's a problem here. My second Go routine is locking M2 first and then M1. When I run this, it's going to fail. Okay? Why does it fail? Now, for some of you who've been to school, you're going to see this and recognize, and you're going to think, dining philosophers problem. Okay? And the dining philosophers problem in the simplest version is, let's suppose there's two philosophers, a knife and a fork. And in order to eat, you have to have both the knife and the fork. Okay? But there's this problem where if one philosopher grabs the knife and waits for the fork, but the other philosopher has already grabbed the fork and is waiting for the knife, neither one of them can eat because they don't have both utensils. All right? So the dining philosophers become starving philosophers. And the answer to this problem is actually very simple, but it requires some discipline of programming. The answer is you always have to acquire the mutexes in a particular order if you're acquiring more than one. So in this case, if I change this program, so the second Go routine locks M2, and then, it locked M2 first, which was wrong, right? Okay, now I look at these two Go routines, right? And they're both locking M1 and then M2. So if I get M1, I'm going to get M2 because the other program is also trying to get them in the order M1, M2. And if you're not sure about that, just think about it for a little bit. Okay? But if I always lock them in the same order, then we can't get this problem of, well, I've got one and you've got the other, and we're both stuck waiting for the one that we can't get. So when I run this, it's going to succeed. Okay? And it sort of proves that point. And this is, I think, one of the drawbacks of mutexes. If you need, for some strange reason, to have more than one, then you have this complicated problem of making sure that everywhere in your program, you acquire them in the correct order. That's non-trivial. And that's one of the things that makes mutexes hard to use. I mean, the other one, if we go back one playground again, right, we've got this issue of, if I lock them, I have to remember to unlock. And now we've got this new problem where if I've got more than one, I have to make sure I lock them in the correct order. So that, to my mind, is one of the things that make mutexes a little harder to use than the stuff in Go. I can do more things with the Go channels and select and Go routines in an easier way, I think, than trying to deal with multiple mutexes. So now I'm back in the slides to talk about some other things. I'm going to start with the Go routine leak. And we've seen this before, so I'm just going to talk about it very briefly. Okay? But here's an example again, right? I've got some Go routine that wants to write to a channel and I've got somebody else that's receiving it. It's the only receiver, but the receiver can time out and quit. And if that happens before the Goroutine times to send, then we could leak the Goroutine because the channel isn't buffered. And this problem also has a simple solution. When I'm in the situation where the receiver could time out and go away, then buffer the channel. If I put a buffer on here, that means the Goroutine over here is guaranteed to have a place to write its response, even though its response is going to be thrown away because it's too late. Okay, we've had several sections in which I've talked about wait group. And I was very careful always to show a certain pattern. I want to show what happens if you violate that pattern, because there is something important about a wait group that you need to understand, and that is when you're going to go track a unit of work, you add one to the wait group first, and then you start the unit of work. Okay. Now on this slide, I've done it wrong. Okay. My big mistake is I'm doing my add inside walkdir, and this is I'm taking this out of the example from the file walk. If you didn't see that, hopefully this will still make sense. I'm calling this function possibly in a Goroutine. I'm only adding to the wait group after I start the function, and that's wrong. Okay, and I'm going to illustrate why it's wrong here in just a second. Okay. The net effect could cause wait to return too soon. How does that happen? Okay, so here's an example of where it can happen. Right, we started, and if you remember the program, the first walkdir actually didn't have a Goroutine. But let's suppose I've got a walkdir running. Okay, and what it does is the code that I just showed you. Let me snap back. It adds to the wait group, and then it calls defer. Okay, so over here we add one to the wait group, we defer, and then we call a function that's going to call a Goroutine. Okay, that Goroutine starts, and maybe there's nothing else to do in this first version of walkdir here, so it can return. And when it returns, it's going to return wait if there's nothing else left to do, because this other one hasn't started yet. Okay, what happens over here is if I start this other Goroutine to add one, well, the adding one could get delayed. That Goroutine may not get scheduled right away. Okay, so let's suppose I started out with, some number of units of work. I've done all but one. I go to start this last one over here, but counting it is delayed, and so my return to where I'm waiting for waitGroup.wait is going to happen before this add can happen to cause me to wait for one more thing. Okay, and we talked about this pattern, right? A wait group, right? The wait group is done when it gets back to 0. So if you think about this, I added one, and then I added one, and I completed one, and I added one, and I completed one. And what we're worried about is I could complete one and then add one more over here. Okay, this last delayed piece of work, I started a Goroutine and then I tried to add, and that add could happen after I've already done this return to 0 and woken up the guy who's waiting on the wait group. And so we won't wait for this last piece of work. Okay, so we need to always make sure that we do this the right way. We need to always, always, always add to the wait group before we start the unit of work. This next problem we've also talked about. In fact, we beat this to death without even talking about Goroutines. And it has to do with closure capture, and in particular, very particular, closure capture of the loop variable. Okay? And we don't want to do that because we've seen what happens is typically, let's suppose I run this, I may get this print line printing 10 times. Because we rip through this loop and start the Goroutines, and the Goroutines are all looking at I, but when they start, I has already finished iterating, and I is 10. And so all the Goroutines print the same thing. Now, as I said before, this is not a Goroutine problem, and it's not actually a Go language problem. There are other languages that have closures, and they close over variables by reference, and this can happen. It can happen without Goroutines, and it can happen in other languages. All right? It most commonly happens in Go with this pattern right here of starting a Goroutine and capturing the loop variable. All right? And the best way to do that is to change your function to take a parameter and then pass the loop index as the parameter. Okay? And if you can't do that, then there's an alternative where you put some code right in here somewhere, right here before you do the go, you put in something like I is defined as I, and so we create a copy of the loop variable that becomes a local variable inside the loop, and then the closure refers to that local copy and it has a different value for each iteration. So there's a couple ways to solve it. Again, I like the parameter approach if I can, assuming that I'm in control of the parameter list of this little function. And if I'm not, well then I'll do this other approach, and I'll usually put a comment there. I'll put a comment that I'm dealing with a closure capture thing. That's the reason I'm doing it. Now, I've talked about select some. I want to point out a few rules about select, because select is probably the most complicated part of the Go concurrency package. Okay? So first of all, default is always active. That shouldn't be obvious. I mean, it's the default, right? But you got to think about, the problem with select is you come into with this model of what I think is going to happen, and you need to remember what the rules of the language say will actually happen. Okay? So default is always active. If nothing else matches, nothing else is ready to go, you're going to take the default. If you put that in a for loop, then you're likely going to spin and eat up a lot of CPU. Okay? We ignore the channels that are nil. So if there's a channel variable and we put nil in it, then that channel is no longer considered as part of the select. Okay? We skip over any full channel, right? We can't send on a full channel, so we'll skip it. The same way we skip a channel that we're trying to read from, but it's not ready to read because there's nothing in it. Okay? So those will block or they'll pick an alternative. Now, the two things, though, that are most important, and let me start with the last one. Okay? So a switch statement goes from top to bottom. And the default doesn't have to be at the bottom. We put it there conventionally just because it's easier to read. Okay? And we'll put the default probably at the bottom of select. But select does not go top to bottom. If I have several things in a select and two or more of them are ready at the same time, let me use my square quotes, at the same time, all right, then it will randomly pick one of them. Okay, it does not evaluate the cases from top to bottom. That's very important. And the second thing, and it's sort of related to this and this mental image problem, we have the notion of the done channel, and we fixate that like, okay, well, I've signaled done. It should know I'm done. But the done channel is just another channel. The fact that I called it done, it doesn't have any special meaning to the Go program or to select. Okay? And so we just have to think about, okay, what can happen? What are the possibilities? Right? Because it might not pick the done channel first. Or, and here's a possibility, there might be some other channel that still has input, and when we pick the done channel, we're done, if we have a return or a break. And that might be okay. I mean, the intention usually of having a done channel is to abort, to stop doing stuff, and that might mean we ignore other input. Just got to think about that. Okay, so I'm going to walk through a couple of scenarios from real code. They're a teeny weeny bit complicated, but bear with me. So the first one is this case of default, and it has to do a combination of default and this channel that I'm writing to. Again, I'm writing to the output channel. And the model here, again, is I'm doing something like reading from a socket, and I need to feed that through a Goroutine to something else. Great. So the idea here is, the original idea would be, well, for some reason, if I don't want the input anymore, I will set output to nil. As soon as I set output to nil, it doesn't affect anything anymore, and that way we take the default case and get out of here. Well, that's great, except for one little problem. Okay? And the problem is that logic is also going to happen if at any time output becomes full. If output is full, it has no room to push one more thing into that channel, then we're immediately going to take the default case, and any more output from the socket will be lost. Okay? So this is a case of where select can trip you up, particularly trying to be clever and nilling out channels inside select. Got to be careful with it. Now, this is sort of the inverse case. I'm reading my input channel. If it doesn't have any input, then I could select the done channel. And again, most of the time if I have a done channel, it's because I want to abort. maybe I want to abort without losing any input, and that's going to be a lot more complicated. Okay, and this model is awfully simplistic for that, because what it says is if I can't read the input, then there's a possibility we can just stop. And if what I want to do is just deal with the fact that I'm running out of input, then what I should do is probably just arrange to close it. Okay, but then I'll need some other logic. I could change this logic to be x comma OK gets the value of the read, and then look and see if I close the channel, OK will become false, and then I can get out of here. Okay, so that's a different approach that might have worked better. Again, when you look at a select, you really have to think about what are the possible combinations of things that can happen according to the rules. And I want to go back to that slide. You need to remember these rules when you do it, because it's easy, and I fall into this trap. Both of these examples are in my code. I fall into this trap of thinking what I think should happen, and you don't realize that select follows these rules, and in certain cases, it's going to follow the rules in a way different than what you think is going to happen. So I want to end up with some suggestions about how to get around the gotchas. Okay, there's 4 of these. One of them, of course, we've talked about. If you're going to start a Goroutine, know how it's going to stop. Okay, just plan for that. Now, it may be you want to write a program where they all just run until the program stops, because when the program stops, all the Goroutines stop. And if that's all you care about, then you don't really have to think about much. But mostly in a long-running server program, Goroutines come and go as you're doing work, and you need to think about, well, I started a Goroutine to do a unit of work as part of a microservice. I'm handling a request, I started a Goroutine. I need to make sure that when the request is done, the Goroutine goes away. Because if I leak them, then eventually I'll run out of memory. Okay. The second one, and there's 2 pieces of this, okay? I want to acquire locks and semaphores as late as possible, right? And I showed an example of this where I go out and do an HTTP transaction to get a new OAuth token. I don't lock the mutex before that. I get the token, which could fail, and then I lock the mutex, and then I update the object with the new token. So get your mutex as late as possible. If you have more than one, you have to get them in the same order. And we want to release them in the reverse order. And of course, the nice thing about defer is defer goes in the opposite order. If I defer A and B, then B happens and then A happens when the function comes to an end, which means if I'm using defer, my locks will get unlocked in the right order. Okay. The third one is a little trickier. When Go appeared, people started doing weird things with channels and Goroutines because they could. And it doesn't always make sense. So here's a teeny wee little program that starts a Goroutine and waits on a channel to do something that, none of this is required. Because all it's ever going to do is return the value of 1. So why not just program it to return 1? Okay. So think about what parts of your program are effectively concurrent. Start Goroutines for those things. But don't just start a Goroutine without understanding why you're starting it. There's no point in starting it for work that effectively isn't going to be concurrent. And the work here, and this is of course an incredibly trivial example, but the work here is never going to be concurrent, right? I'll go into this function and come out of this function, and there's no concurrency to be had. So why start a Goroutine? Which brings me to my last point, which is of course, the last point is probably the answer to almost all problems in programming. Simplify it, and simplify it some more, okay, until everybody can understand it very clearly. Review it. Get some other people's eyeballs on it, particularly if you're new to Go, people who have a bit more experience working with concurrency in Go, because they'll spot the mistakes you won't. And of course, test, right? And I'll talk about this again. I think it's fair to say you should assume none of your code works unless you've tested it. So that's a brief introduction to the gotchas of concurrency and concurrency in Go. It's not a lot, but it's a starting point, okay? And that paper I referenced, if you want to go a little further, has a few examples of people combining like a select and a mutex and so on and getting themselves locked up. Again, keep it really simple, review it, and really think about what it's doing, right? And test it.